Good day to you all. My name is Aleksandar Pajkanovic and I'm very happy to take part in MIEL conference after almost a decade since my last presentation. I'm here from Banja Luka, Faculty of Electonic Engineering, University of Banja Luka, to present a paper titled Open Source CMOS General Purpose Operational Amplifier. After an introduction, I will take some time to explain the motivation behind this work, and then I'll dive into tools, technology, and the actual example design that is going to be the, let's say, a vehicle of this idea. Finally, we'll draw some conclusions, hopefully. The general topic of semiconductor industry is a wide known matter, since this actually represents the workhorse that has been driving the information age for the last 50 years. So the integrated circuits, or the chips, are something that are omnipresent, even though the end user may not be aware of them. However, we are, so the three components required for an integrated circuits to see the world are, well, of course, the idea, a schematic, a topology, the circuit that we need to materialize, and then we need the software tools. Of course, we're talking about the designer's side, we're not talking about the tools that are actually used in the foundry to create the layers on top of silicon or other substrate. And then the final part is the project design kit, or the PDK. So that's basically the description of the devices that we can use within the software to realize to implement our idea, our schematic. So even though the ICs are omnipresent, only a very small minority of vendors, of companies, of even individuals could actually stretch out to the point that they can actually reach and grasp all three of these pieces. So let's briefly look at each one of them. So the ideas, so the ideas are available in the textbooks, let's say, and those are found easily enough. So these are found easily enough at a reasonable price. So check. The industry standard tools are, on the other hand, so expensive that only a number of vendors may obtain the licenses. So there we actually, in most cases, fail to get our hands on industry standard software tools. We also fail to get the project design kits in many cases, because first of all, getting it is a terrible amount of paperwork, and they don't even conclude these contracts with just anyone. Even if we do it as a university, then we have a limited application. So that's a fail again. But as it will turn out, or as it has turned out, and I'm going to remind us about this in the next slides, we are actually living the revolution, the technology revolution, and this is because this is for the first time in the history that all three pieces may be collected free of charge and drive us to actually silicon proven designs. So looking over the three pieces again briefly, it turns out that open source software IC EDA tools have matured enough, carried on the wings of the open source hardware community, and backed up by the industry or some of the main industry players, and we actually have seen chips designed by open source software tools. So this is actually silicon proven, so we can say that it's actually check for the tools. We can get the tools for free. And the latest thing that happened just last year in 2020, Skywater, a subsidiary, created by a subsidiary of Cyprus, open sourced, meaning released publicly, the 130 nanometer CMOS standard process node, or its PDK is now open sourced. Therefore, we have a PDK that is freely available. And when I say free, I mean free of charge, as well as freely open sourced. So what do we want to do? So we want to learn, build, and grow upon the facts that mature nodes perform very well in so many areas where low cost, low power consumption, and stability are of interest. And since this this movement has been spreading around the world, we want to join in and demonstrate the real silicon examples designed using free tools are feasible. We also want to popularize these tools, technology, and electronics in general. And finally, we want to build a world-class university-level course here at the Faculty of Electrical Engineering in Banja Luka. So these are the tools. They are explained in a bit more detail in this and some other papers that I have authored in the recent years. So I will let the readership get the details from there and just move on to the technology itself. This is a brief overview. For more details, please do check this GitHub link. Let me just point out quickly that Google, in collaboration with Skywater, has been sponsoring shuttle MPW runs. So you actually get even the fabrication free of charge. An industry player that really deserves to be mentioned is eFabless, and their crew that has enabled this, of course, along with plenty of others open source contributors. But please do check eFabless. So these are some insights into the performance of the technology. I will not stall on this. I'll just briefly mention that the contribution of this paper does not lay in the circuit theory. There is nothing novel in the context of the circuit design. Rather, what we contribute with this paper are the scripts, the schematics, and basically all the source files, all the files required to regenerate these graphs and continue on to the design of an operational amplifier. So designing an opamp actually requires a specific set of skills that we are trying to teach students in the IC related courses, in the VLSI courses. So this is specifically related to analog design, and designing an op-amp is a sort of a project, a journey that is very well suited to discover how well the student has acquired this set of skills. So we need the general purpose template to set a pattern and compare. So it's just a standard two-stage topology. You can find it in any IC standard basic textbook. For details, please refer to those or one of our recent papers. Aside from the scripts and post-processing code in Python and graphs that you have already seen, there's also complete layout of the op-amp available at our repository. These are the results. We can see the minimum and maximum at the input and the output of the circuit. This is the magnitude amplification of about 50 dBs, and the phase margin is somewhere at 75 degrees, whereas the transition frequency is 100 megahertz. This is the behavior in the transient analysis. And finally, the layout. Layout is very basic, no advanced techniques whatsoever. So this is something that we plan for future work. In order to avoid low power supply consequences and short channel effects, we wanted to focus on methodology, and hence we have selected the transistors devices that operate at pretty high voltage, 3.3 volts, that are limited to a minimum channel length of 500 nanometers. Of course, there are transistors that work at 1.8 and are limited with 130 nanometers. We also use resistors and capacitors in order to be able to discuss pros and cons of these passive components in the ICs. As mentioned, all the contributions are available online free of charge. In future, we hope to provide more metrics like power supply rejection ratio, common mode rejection ratio, and so on. We would like to include Monte Carlo simulations with ngSpice and touch up on the layout with matching and advanced techniques. For any questions, I am at your disposal. Please do contact me. Or even after the conference, please do use this email to discuss anything you might find interesting related to this paper, or propose collaboration in any context that you find useful within your own research and teaching area. Thank you very much for your time. All the best. Goodbye.